We are going to first, sorry, I have to reopen everything I just shut down. We're going to first look at the previous homework because I'm sure there's at least a few questions on that, and I want to make sure we address them before we go on. So let me open up the key there. Um, I'm just reopening everything that I had to shut down, unfortunately. Oop, more customers. All right. Oopie. What did I do here? So, yeah, there's at least one that I want to go through just because it's instructive in a different way about like the math aspects. But for sure, let's take a few of your questions. And then today's primary lesson, and sorry I'm showing you the other class's schedule. It's the same as yours, just the days are offset. This one opened first. But the plan right now is today I'm going to cover most of solubility product constants. There'll be another problem set. You won't be able to do the whole thing unless you want to read ahead, but I am assigning it because we basically have a whole week before we meet again, right? Because of all the days off and then the Wednesday and then whatever. So I just want to make sure we don't fall behind on that. But I did make some adjustments so that instead of giving you the test on this Wednesday, the 24th, I'll probably put it like a review quiz there and then assign the test to be over the weekend, that weekend. So we have some more time, a little bit, without losing time, as it were. Um, yeah, so let's look at the homework first, and then we'll go from there. And I saw already in the chat a request for 4A. So let's look, because some of these, again, I picked because they were interesting twists on the situation. So let me just kind of grab it and put it in the document to write on it. Oop, somebody's chatting at me. Yeah. So I'm kind of going to follow my time and do as many of these as I can with you. And then if I run out of time and I have to shift, I'll let you know. So for this one, it asks what would be the pressure. And I like this problem because we've been doing mostly concentration, but this shows, we apply the same methods if we're doing pressure. So we have this situation, and I will set up the ice table here just to kind of see what it looks like. Again, this is just a nice organizational tool regardless of the problem, just to keep track of where things are. So we're given the temperature, we don't need that. We're given the equilibrium constant, so let's go ahead and write the expression. It's going to be the pressure of PCl3, the pressure of Cl2, all over the pressure of PCl5. And remember, pressure is measured in atmospheres, so if they're not given in atmospheres, they have to be converted. We're also given a volume, and we're given a mass. So this says, suppose that this much solid is placed in this volume. So what they're telling me is the initial amount, right? It's not the amount at equilibrium because we're just putting it in and seeing what happens. So this says, what would be the pressure of PCl5 if it did not dissociate? Well, we're just doing PV equals nRT, right? In other words, we're not even talking about the reaction yet. This is just a review concept just to establish what the pressure is. So to do this, we need to put our liters in here, which is 500 milliliters is half a liter. The moles is going to come from converting the grams of PCl5, which is about 208.5 grams per mole. The temperature, I guess we did end up needing here because we're doing a pressure problem. And then, of course, our gas constant, in order to force the units to be atmospheres, we have to use the 0.0821. So just a nice review of ideal gas law in general. Now, I'm not going to go through the math here. I mean, it should be evident then that we're going to get a pressure. And when we solve for that pressure, as you can see from the key, it comes out to about 1.158 atmospheres. And that's really what we need, that answer, to now establish this problem going forward. Because now we know the initial pressure of this, meaning none of it had broken down yet. And because we're not mentioning these other gases, we assume they're not present. So that's really what part A is about. Did that answer that question? Oh, sorry, you had said 4D, not 4A. I just went through all that for nothing. Ah. All right, anyway, so let's assume you got that far. You went through the whole, okay, well, we chased the zeros, so we don't really need to calculate a q. We know this drops x plus x. And then we have, 1.158 minus x, and you go through the whole process and you solve for x. Well, this, just think about what they're saying. Isn't x the amount of this that breaks down, right? Like from this interpretation, this is, oh God, what was that? This is saying literally x is how much reacts. So literally to figure out what the percent of it dissociates or breaks apart is, you're going to take what you get for x and put it over this initial amount. You can do that in terms of pressures. You can convert it to grams and do it in terms of grams. It doesn't really matter. But in the end, you're going to put the amount of x over the starting amount and then see what percentage you get from there. Does that make sense, Miriam? Yes? All right, let's pretend it does. Anybody else have a question about that? Oh, no. Okay, go ahead. What's your question?
So would I put, so you said put x over the initial amount?
Yeah. What did you get for x?
Um, 1.079.
And that's in atmospheres, right? So this
Mm-hmm.
much dissociated, right? That's what x means. It's how much of this reacted.
Mm-hmm.
And if I put that over how much I started with, isn't that the percent of it that dissociated?
Right. Okay.
That's all.
Okay. Thank you.
You got it. Let me take a peek at number 5. So was there something specific about number 5 that was troublesome? Just so I have an idea what the issue was, like so I can address it directly. I think probably it's the way it's phrased, right? Yeah, so all you really have to do is, since you're given a mixture that's already at equilibrium, right? There's really no problem to solve. But what they're saying is we're going to change the initial mixture. We're going to add this much fluorine. So all you have to change to solve this is you still have this much hydrogen at the beginning. You still have this much HF at the beginning, but now you have to add in zero point 0.2 moles of F2, which means zero point 0.2 out of 5 liters, right? So we can calculate the molarity of F2 that we're adding and just add it to this 0.01 molar, and that's really just your starting row. So it's just asking you to spike the fluorine at the beginning and add it into the total at the beginning of fluorine, and then solve the problem like any other problem. Mm-hmm. So that takes care of that one. Um, Number 8, I think I may have already solved for you because of the percentage issue. So it really is the same that we just did in 4D. Okay? It's literally the same idea. So take a look at it again and see if that works. And then I wanted to go over number 7 because I thought there was something interesting about it, especially if you tried to use the solver. You probably got stuck. It messed you up. Like it was giving you like no sign change or some error message. So let me, just for the sake of argument, let me go over this one. This is the one I wanted to go over because I think it's really interesting how it combines the math with the concepts. Like if you interpret the problem correctly, it'll make sense why things didn't work and how to fix it when this happens. Whoops, too far ahead there. All right, so let me start from, somebody pointed out earlier too that this is wrong because it's not a double arrow, which is correct. Oh, well, that messed up. Let's try that again. Close enough. All right, so just to kind of build the problem right away, I mean, this is pretty straightforward at the beginning. It's really the math I'm interested in that kind of goes south on us. But if you go through the process and set up your ICE table here, phosgene, it's actually one of the early chemical weapons used in warfare. Um, So we're told the moles that we have to obviously turn into molarities. So based on 2 moles out of 5, so that's 0.4 molar here. This one's 3.5, so 0.7 molar, and then initially 0, which means we go this way, which means we lose x, lose x, and we gain x. And then this is 0.4 minus x, 0.7 minus x, and x. So far, everything looks exactly like we've been doing. The expression, again, we're working here this time in concentration based on the k we're given, is going to be just the concentration of the product, first power. I mean, this should start feeling pretty automatic at some level. And then the expression we have to solve puts k, which is about 1230, and then we enter our expressions. Okay, so we're here. Now let me bring in my calculator, because I'm going to just do what I showed you how to do. I'm going to take my calculator and I'm going to enter this into my solver in the math section. And if you don't even have this kind of calculator and it's troubling you, you can always find these solvers online. You can literally just Google polynomial equation solver, and you can do what I'm doing on the calculator effectively on the computer. But for now, I'll use the calculator because that's what most of you have. So x divided by the quantity, and I have to double parenthesis, 0.4 minus x, close that one, 0.7 minus x, close that one, close the whole thing. I'm subtracting the constant. And then we've been saying, your best guess is usually around 0. So I put in 0 here, I hit my alpha enter to solve it, and the first thing I notice is the calculator takes a while to think about this one. Usually that means it's searching for that intercept, it's looking for the zeros of the functions, looking for the solutions, but it's having a hard time, and now we get this no sign change. What that's telling me is where this was looking, it couldn't find where it went from positive to negative, in other words, where it crossed the axis. It can't find the solution. That means we're not looking in the right place. But could we have predicted this problem? Let's take a look. So when I look at the nature now we're looking into the physical nature of the problem. What does the value of k, in this case, tell me about what this system will look like at equilibrium? It's a large value of k. What does that mean? One at a time, please. Oh, it's coming across on the chat. Oh, 2 chatters. Oh, more products, mostly product. That's exactly right. This is saying that at equilibrium, most of the reactant should be converted to product. We should have mostly products. But then if that's true, what is the implication for what x should be? Does x being close to 0 make any sense under those conditions? You get what I'm saying? Like, doesn't this tell me how much of the reactant gets used? So x should not be close to 0. What should it actually be close to? Look at the stoichiometry of the problem now. What's the value that x should approach as k approaches infinity, just to kind of use the mathematical language?
Infinity?
I wouldn't say 1,000 and I wouldn't say infinity. Again, look at the physical nature of the problem. The reaction can only go until what happens. Theoretically, remember before we studied equilibrium and we only studied stoichiometry, what limited the reaction? When did it stop? Just in the general sense. Oh, I should just leave the chat open. when the reactants are finished. Exactly. Now, based on the ratios in this problem being all 1 to 1, which of these two reactants are we going to run out of first? We're using them at equal amounts, equal rates, but we don't have equal starting amounts. Exactly. And so the most X could possibly be, theoretically, would be 0.4. In other words, X should approach 0.4 in this problem as K gets bigger and bigger, because we're saying more and more reactant is being converted. So the assumption that X equals 0 does not make sense here physically by the nature of the problem, meaning because of the size of K. And so now if we do this, check this out. If we go back to our calculator, we can't put 0.4 as our guess because then we'd be dividing by 0. That's not going to be allowed. So let's just put it close. Let's say 0.39 based on this physical problem makes sense. It's close to using up all of the carbon monoxide. Now when I put in my solver, it finds the root I'm looking for. It tells me that X, in this case, is about 0.399, which is logical to what we just said because it's very close to having used up all of this reactant. And now we can use it to calculate everything at equilibrium. So I like this problem because it threw that wrench into the works and forces you to think about the physical aspects of the problem, not just to blindly try to calculate the math. So I just think it was instructive. Any questions about that? Okay. So now we're going to turn our attention to really just extending what we've been learning. Everything I'm going to tell you today, we've already learned. We're just going to put it in a different context. And again, if you just stay steadfast, yeah, theoretically, Miriam, if we're talking equilibrium, we never officially get to zero reactant, right? I mean, there's always going to be some, otherwise you can't have equilibrium. So it will approach zero, but we'll never say it's truly zero. um, so the context we're going to use now is something called solution equilibrium, which really deals with solubility and Ksp. So it's an equilibrium constant, but it's given a specific name. This is called a solubility product constant. It's just another specific type of equilibrium constant. So you might ask, logically then, what is this referring to? What is in equilibrium with what in these specific cases? So typically we're going to have an ionic solid on the left side, and it's going to be in equilibrium with its ions in solution. And just, I'm trying to make this as generic and hopefully understandable as possible. So what we're saying then is, if we look at the forward process, that's what we call dissolving, right? We studied some of this in Unit 2 way back in first semester. We talked about solubility, solubility rules, predicting precipitation. But back then we hadn't learned the tools of equilibrium. And so we made it kind of generic. There was an arbitrary line we drew in the sand and said, well, if this much at least dissolves, we call it soluble. And if it doesn't, we call it insoluble. And we use that table of predicting. Now we can really zone in with equilibrium to understand that solubility is a continuum, not a yes or no question. Well, what's the opposite of dissolving? What do we call it when ions meet in solution and form a solid? That's what we've been calling precipitation. So these are the opposing processes that we're talking about when we talk about this type of solution equilibrium. It's really about the solubility, and I'm going to put here, of slightly soluble salts. Just try to say that 10 times really fast. Slightly soluble salts, I can't even say it once. So when we talk about solubility of something like sodium chloride, I mean, that's so soluble. We're talking about like 35 grams of salt dissolves in 100 grams of water. That's a ridiculously large amount. So we don't talk about equilibrium there, but we can. Let me show you what I mean. I've got some little simulation visual things. You know I always do, so why not this time? Here it is, I think. Let's hope. Boom. And I want you to visualize on the molecular level what I mean by this situation. It's kind of funny how they do this too, because they literally use numbers that are on the submicroscopic scale, but we can still calculate like a typical molarity from this, if it will eventually open. Well, see, this is why I usually have everything ready before class. And then my computer farts on me, I have to start it over. And I have to wait for these dumb things to get sorted out. Boom, boom. Wow. It's almost like I meant that, right? That was amazing. I was so good. Oh, it's still not really going. Ah, here we are. So check this out. First of all, I love these programmers because they always put these silly little bits in. Shake me, and they actually have a shaker. Notice the volume that we're working in is 5 times 10 to the negative 23rd liters. We are literally working in the submicroscopic level. I'm going to shake some salt in there. There's the crystal. It dissolves. Not very mysterious. This is salt dissolving in water. The ions are free. We call these electrolytes, all that sort of stuff. But this is not an equilibrium because it just all dissolved. There is no reverse process yet. Why? We haven't reached the maximum that can dissolve. There's a name for that, by the way. When you have a solution that's maxed out, that can't dissolve anymore, we call that solution saturated. Right, sorry, this is kind of laggy here, so you can see I'm having a hard time. It's my computer's arthritis is making it hard to shake the salt shaker. But I just want to put enough in here until we get to the point. I might have to just do this. I'm just going to do it this way for now, because I know it's going to take more. But you can see in this little space here, it's keeping track of the number of ions that are dissolved versus the ones that are still locked together in the solid state. And so far, everything I've put in just keeps dissolving. All right, let's dump a little bit more in there. I mean, there's got to be a limit, right? At some point, we run out of space, and there's just nowhere to put these ions. That's what ultimately is going to determine, to some degree, how much we can finally get in here. But you can see I'm dumping in quite a bit, and it just keeps dissolving. No equilibrium still. But there's a limit. Eventually, the solution will saturate, and that's what I'm trying to get to. And this is right now table salt. Like, this is a really soluble salt. So we don't even think usually in terms of equilibrium. Man, this is laggy today. Am I even close? Let's see. Nope, it's still all falling apart. You can tell again because everything I'm putting in dissolves. Come on, shake, dude. Give me some salt here. Really? We're going to be here for a while, folks. I hope you don't have any plans. I'm just kidding. It really shouldn't be taking this long, but it's like, man. Eventually, what we should see is that some amount stays dissolved, but no matter how much more I add, it's going to stop dissolving. Will I ever get to that point this way? I don't know. Maybe I should just crank it up some more, because I think this is taking a long time. Let me kind of boost it on this end until I know I'm past that point. I think I'm getting close. I think I am. I think I am. Oh, wait a second. I think I've hit it. Notice now that somewhere in this system, there's a piece of crystal that's not dissolving anymore. And that if you look at the count here, we're keeping about 180 particles dissolved of each, and anything extra staying bound together in the solid state. So what we're saying is that as fast as these ions are dissolving, new ions are reforming the precipitate. So it's not changing anymore. Now we have established an equilibrium, and even if I add more salt at this point, it won't change any of the concentrations. Why? Because the solid can't dissolve anymore. Do you get what I'm saying here by what I mean by this kind of equilibrium? Does this help you visualize it, even though it's like, I feel like I'm working on my old Commodore VIC-20 computer from 1982. All right, let me get out of this one and move over to a different salt because this is really starting to boggle my mind. This is really just laggy here. Hope the other one isn't as bad. So here now, we're going to look at what's the difference if we look at something that has much lower solubility. So you'll notice here I have a lot more water, 10 to the minus 16th instead of 10 to the minus 20 there. Wow. And I'm going to take almost the same kind of salt, just a positive and negative 1 ions. But this time, the Ksp, the solubility constant, is really small. So let's shake some of this in here. Oh, it's coming in a lot easier now. Look at that. And again, it starts dissolving. No surprise. But, and this is a big but, we're going to reach the limit a lot sooner. We're going to saturate this solution with much less of this salt because it's less soluble. What tells me that? Well, in large part, the Ksp does. And already you can see, what do I have? Only 40-some particles dissolved in a lot more water. And we're starting to get close to the edge here, I think. Let's see. Did that do it? Nope, not equilibrium yet. This is a lot better when it actually works smoothly. It's taking too long. All right, check this out, though, because it really is useful, I think, to make a point about it. So right now you can see 60 particles dissolve, and anything more just doesn't. We hit equilibrium. Here's my question. What do you think would happen if I was to take this system now, this salt, and change it so that the Ksp went higher? What if I made the Ksp constant a larger value? What do you think we would see inside the container? Oh, somebody said something. You're saying more will dissolve. Let's see if you're right. I'm literally going to increase it by a factor of 10 and just watch the container. It's all dissolving. And we could add more. On the other hand, if I make the Ksp even smaller, let's go the other way by a factor of 10. Now it's become far less soluble, and what you should see is precipitation starting to happen. And we're going to reach an equilibrium eventually, but with much less dissolved particles. Because the less soluble it is, the less of it can dissolve in the water. And you can see it starting to crystallize and precipitate all around, leaving less and less ions behind. So the Ksp is intimately tied to the solubility. Now we have to look at how equilibrium lets us make this a predictable system. So I'm not going to keep watching this because it's driving me bananas that it's going so slow. So remember, the term saturated solution is important here. When we reach this equilibrium between the solid and the ions in solution, we have a saturated solution. And that means no matter how much more salt we add, it will not dissolve anymore. Question is up. No, you have it backwards. The higher the Ksp, the more dissolved. The solubility increases. But we have to qualify that a little bit because it's a little more complicated. And so that there's no doubt about this, we're going to see it in the mathematics coming up now. But it's a little trickier than just a simple statement because it depends on how many ions are in the compound. You'll see that now. But first, let's look at writing these kind of expressions. So we're going to now take this generic format and we're going to do it with real problems. So writing Ksp expressions. It's just what we already learned with equilibrium expressions in general. But these are heterogeneous because they're solids in equilibrium with ions dissolved in solution. So let's consider, for example, something like copper iodide, which is a solid, and it forms a saturated solution in water between its ions and the solid crystals. So we've added enough of this copper iodide solid in order to establish an equilibrium, to saturate the solution. We need a Ksp. Well, lucky for you, somebody who works in our district that teaches this class and is sitting right now on the computer with you had the foresight to put a Ksp table on his website. So when you need to look up the values, they're there. There's a pretty extensive number, and this isn't every possibility, but we can at least look. You can see these are all numbers much smaller than 1, which is kind of important. But let me find copper iodide. Gotta be here somewhere. Copper iodide. Here it is. 1.27 times 10 to the minus 12 is its value. And this is tied to a specific temperature. Since temperature affects these values of these constants, this is meant to be at room temperature. Oh, how sweet. I'm sorry, I'm looking at the chat. It's hilarious. Okay, now, if I said, let's set up an ice table on this, and I asked you for the following, here's the questions we would answer. Let's use this expression and this constant to find the concentrations of these ions, but also to define the solubility of the compound. And the solubility, which is just a way of saying how much can dissolve, can be expressed in 2 different ways. Typically, it naturally is going to come out as molarity, right? So we'll figure out how many moles dissolve per liter, or we'll often convert that into grams per liter. Sometimes it's easier to interpret that way. This is just obviously using the molar mass to do the change, but I'm just saying this is what I'm looking for when I say, let's find the solubility. Well, how do we go through that process? You guessed it. Ice table. Okay, anyway. And we saw problems like this. I purposely seeded this in the last problem set and said, oh, this is one of those enough problems, right? So this is saying as long as we have enough to establish equilibrium, enough solid. And let's start with doing this in pure water. So we know that there's no other of these ions present already. It's just we drop the solid into the pure water. Well, we know that, again, it's going to chase the zeros. So X of this will dissolve. X of these will come into the water. And then we don't care here, but we can now set up this problem. Now we can talk about why is Ksp called a solubility product? Well, let's think about what the equilibrium expression looks like. Wouldn't it just be this? Why am I leaving the copper iodide out? Why is there no denominator here?
It's solid.
Good. And so every time we do one of these kind of problems, an equilibrium between solid and its ions, this will always be the case. It'll always just be the product of ions. Therefore, it's called an ion product or solubility product constant. That's why the terminology. They're always going to look like this. The only difference is if there's different numbers of ion ratios, that's going to affect our coefficients and that's going to affect the exponents. That's the only difference. And so solving this is quite simple because, again, all we need to do is this in this specific case. And I would plug in x into x, which is x squared, right? And if I square root both sides, I get x equals 1.1 times 10 to the minus 6th. Now, let's ask ourselves, what does x represent in this problem? What does x actually mean? Because it means a bunch of things. What does this mean? Well, it looks like here it's the amount that dissolved. Therefore, x is literally the solubility of the solid in moles per liter. X is literally solubility. But in this case, it's also the concentration of the ions. So just by the nature of our first example, the concentration of the copper has to equal the concentration of the iodide in pure water, once, because we just got from the same source, has to equal this amount. And so this is the molarity of each of these ions, but it's also the amount of this that dissolved. Why are all these things equal to x? Because these are all in a 1-to-1 ratio. But x is always the solubility in moles per liter. If I want to change it into grams per liter, well, I just have to do this. I have to take my moles per liter and multiply it by the grams per mole, which is, of course, the molar mass of copper iodide. In our case, that's about 191 grams per mole. And so if you're asked to figure this out in grams per liter, that's all you have to do. Multiply your answer by the molar mass. I get about 2.1 times 10 to the minus 4th, grams per liter. And so that's kind of our first example, that what I'm hoping is that you see this is just like the problems we've already been doing. All we've done is put it in a specific context related to solubility. The expressions work the same. The ice tables work the same. We're just adding this interpretation. Let me pause here and see what you think so far. Questions, comments, balloon animals, whatever. Overwhelmed. Oh, wait. Something's coming in. Getting a message. I got an I'm good. All right. As long as I got one I'm good, I can live with it. And the bigger question, how do you get an emoji in the chat, of course. All right. Now, the next thing I want to show you is very interesting. What would happen, do you think, if I was to change the conditions of the problem a little bit? So what if instead of starting in pure water, I wanted to dissolve this same substance. Sorry, this is really starting to get glitchy, so I'm going to change pages. Hopefully you wrote this down. So what if I wanted to do the same exact problem with one minor difference? So let me reset it up. But this time I want to see the solubility in, let's go 0.1 molar Ki, potassium iodide. Will this make a difference? Like, should it matter that I'm putting it in something that's not pure water? And if it does matter, how? How do we take that into account? So let's still again start with, okay, we're going to put whatever this needs to be. Well, let's see, does anybody have a comment on this, or are we still talking oh, we're still talking about emojis. Of course. But seriously, folks, here in pure water, it was 0, 0 of either ion that was part of the system. But here, I'm telling you, we're going to have a solution of potassium iodide. Does it make a difference? Well, the potassium doesn't, right? It's not part of the system. This is just a spectator. But this iodide ion now is going to be present before we start. So instead of starting with 0 of both, now I have 0.1 molar iodine in my system. Again, we've done problems like this, where we start with some of one and not the other. We know it's still going to go this way. We know we're still going to lose X, and gain X. But the difference this time is that we have a term that's not just a simple X. We have another number. So before we even solve this, do you think the solubility of the copper iodide will be greater than, less than, or equal to what it was in pure water? Will it make it easier to dissolve if there's already iodine, or will it make it harder for it to dissolve? What do you think? This is a guess. I mean, based on whatever reasoned principles we've talked about, but you're guessing harder, so you're predicting that the solubility should be lower. Let's see if that makes sense. Well, our equilibrium situation hasn't really changed in the sense of the formatting. It's still the same expression. The difference is what we plug in. I think we said this was 1.27, 10 to the minus 12. This is still x, but this is 0.1 plus x. Now, when you look at that, you might say, oh, great, another quadratic. I got to get my solver. No, you don't. Look at the physical nature of this problem. K here is really small. X should be close to 0. In fact, I don't even have to guess at that. In pure water, look at what X was. It was 0.0000001. It was really small. Imagine adding that to 0.1. It doesn't change it much. So here again, we can make a simplifying assumption that because X is so small compared to 0.1, when we solve this, we can make the approximation that we can drop this X, and then all we have to do is divide the 0.1. Now we get 1.27 times 10 to the minus 11th, and this is again molarity or moles per liter, which is a lot less soluble than it was in pure water. In pure water, so this is in 0.1 molar potassium iodide, with this being the common or key point, whereas in pure water, we found it was, what was it? 1.1 times 10 to the minus 6th. I mean, that's a huge difference. The key to this is something called the common ion effect. That's what you're seeing here, mathematically and conceptually. You're seeing that when there's a common ion, and by common ion, I mean it's one of the ones in the solid that we're dissolving. See, that's why potassium is not. But if it's a common ion and it's present, it affects the solubility. In fact, we can see directly from our calculations is that a common ion decreases the solubility. That's what this example was meant to reveal. That's a general conclusion we can draw from this example. Now, I'm going to do one more problem today, and then I'm going to tell you that the problems that I assigned, I think there's like 12 of them. You can do the first 9 just from our lesson. The other 3, you might have to figure out on your own, but I'm going to talk about it next time, because there's no way I'm going to finish all this in one period. So I'm going to ask you, don't submit your next homework assignment right away. Just have done what you can by next time. So when we finish the lesson, you'll be in a good position. But here's what I want to ask you next. Let's pick a different solid. Let me go back to my table. Just let's pick one with a different number of ions because I think we need to make a point about it. I'll take iron 2 hydroxide, I think. Does that look good? Yeah, that looks good. And let's just ask the question, what's the solubility of iron 2 hydroxide in pure water? So just so we can understand what we're comparing, what did I just say that was? Sorry, I might go over a minute or two, but that's because of my technical difficulties. Otherwise, obviously, my planning is perfect. I'm looking at the wrong thing, sorry. 4.87 times 10 to the minus 17, 4.87. Come on, pen. Whereas earlier, when we did the copper iodide problem, we said the KSP was 1.27 times 10 to the minus 12. Now, based on these numbers, if I said which one is more soluble, your first instinct might be to say copper iodide because KSP is larger. But we can't make that comparison directly. The only time the KSPs can be directly compared is if the number of ions is the same. In other words, when I look at copper 1 iodide, which has 2 ions, and then I look at, say, copper 1 chloride, which has 2 ions, I can directly say copper 1 chloride is more soluble because of the larger KSP. But that's only because the number of ions matches. You might be, well, why would that matter? Let's do the ice problem for iron hydroxide and see what happens, because it might surprise you. It looks, again, very much the same. But notice now, based on the ions in the compound, we're going to get a different ice table. Let me just dispense with writing the lines in for now. And we'll do pure water so we can compare apples and apples. But like I said, I'm trying to highlight the fact that my methods are the same as we've been learning all along. There's really nothing different here in terms of method. But this time, notice that our expression is going to include the iron, but the hydroxide is going to be squared. And that's why the number of ions influences the final outcome. Because now if I take my x and put it here, and I take my 2x and put it here and square it, I'm going to get 4x cubed. Oh my gosh, is this falling apart? 4x cubed on this side, and I'm going to get the constant on that side. So when I solve this one, I'm going to have to take this 4.87 times 10 to the minus 17, divide it by 4, and then take the cube root of that, because it's an x cubed, right? Remember, we take to the 1/3 power. Well, I get about 2.3 times 10 to the minus 6 for x. If you recall, the copper iodide was 1.1 times 10 to the minus 6 for x. So it turns out this one is actually a little more soluble. But we wouldn't have expected that based on the KSP. And so the moral of the story, the note to write down, is that I can't just look at KSP for solubility unless the number of ions matches. If it's a different number of ions, I have to go through the whole calculation to know which one is more soluble. And on that, this lesson ends today. So try the homework that's assigned. Again, you don't have to submit it, but I won't see you for a whole week, basically. So I want you to at least work at it. And then if you need me between now and then, come and see me. And of course, at 2 o'clock, I'm going to start the next session for the extra sessions for those who can attend, and I'll record it for those who can't. What I mean by the number of ions is, for example, if you have like we had copper iodide like this, it only gives me 2 ions, right? 1, 2. When I had FeOH2, it gives me 2 of these and 1 of these, which is 3 ions. And every time the number of ions changes, the coefficients in the equation is going to change, and it's going to affect the power to which I'm raising x and the final outcome of the calculation. If I had something like calcium phosphate, this has a total of 5 ions that are generated when it dissociates. Yeah, thanks for asking that. So yeah, that's it for this one. Like I said, you're just going to have to give it a whirl. So I'm going to stop.